An orally administered drug enters an environment engineered to destroy foreign molecules. To reach its destination, it must survive a hostile gauntlet of physiological barriers. The primary obstacle course is brutal. The molecule must endure corrosive stomach acid, navigate an ecosystem of intestinal bacteria, and physically cross the tightly packed cellular wall of the intestinal epithelial lining. Even if the compound survives the gut, it immediately enters the hepatic portal vein. This route leads directly to the liver, where a filtration system of specialized enzymes is designed to dismantle and neutralize the drug. As the remnants circulate, they face distribution traps. Active transport pumps in the liver attempt to shunt the drug into the bile duct, while the kidneys constantly filter the blood to excrete water-soluble compounds into the bladder. For non-neurological drugs, there is a final hurdle: avoiding restricted zones. The molecule must be designed so it does not partition into protected areas, like the blood-brain barrier or a developing fetus. A pill functioning properly is a result of precise engineering. Successful delivery requires mathematical navigation of these barriers using specific rules of molecular design. A molecule's survival through this cycle of absorption, distribution, metabolism, and excretion, or ADME, is dictated by its intrinsic physical constants. This diagram illustrates the three foundational determinants of drug behavior. The first is pKa, or the ionization constant. This value dictates how a molecule will react when exposed to the extreme pH shifts between the stomach, intestine, and blood. The second parameter is lipophilicity. This measures how well a compound dissolves in fats and nonpolar solvents, which determines how a molecule interfaces with biological lipid bilayers. The third is solubility. A drug's ability to dissolve in water is a composite property, depending on its pKa, its lipophilicity, its molecular weight, and the physical state of the solid matter itself. Solubility determines the initial potential for absorption. If the compound cannot dissolve into the fluids of the gastrointestinal tract, it remains a solid mass and passes through the body unabsorbed. These three properties exist in a state of interdependence. Altering a molecule to increase its lipophilicity will typically decrease its aqueous solubility and shift its ionization profile. The primary job of a medicinal chemist is to balance this physicochemical triad. They optimize these specific numbers to route the drug to its target while avoiding the body's metabolic traps. Let's focus on the first major physical wall, the intestinal epithelium and membrane permeability. To enter systemic circulation, molecules must physically cross the hydrophobic core of the lipid bilayer. This cross-section of a cell membrane shows how a molecule's properties dictate its entry path. The red spheres represent a lipophilic drug. Being fat-soluble, they slip directly through the membrane via passive diffusion. Passive entry requires an unionized neutral state. If charged, it's repelled by the oily hydrophobic core. Contrast that with the blue spheres, representing hydrophilic or highly ionized molecules. These charged molecules are repelled by the lipid bilayer. They are entirely dependent on carrier proteins and active transport mechanisms to be pulled across the barrier. Relying on these channels creates a vulnerability. Active transporters can become saturated or subject to competitive inhibition, which limits the total amount of drug absorbed. The local pH of the GI tract interacts with the drug's pKa to determine the exact ratio of ionized to unionized molecules at the absorption site. This relationship is the basis for the pH partition hypothesis, the primary model used to predict absorption efficiency in different segments of the duct. Increasing lipophilicity often improves passive absorption, but it risks lowering solubility to the point of precipitation. If the drug precipitates, it cannot reach the epithelial surface. Precise design is required to ensure enough drug remains dissolved in the GI fluids to actually interface with the intestinal wall. Optimal absorption requires a calculated compromise: enough lipophilicity to passively cross the membrane, but enough solubility to remain dissolved in biological fluids. Crossing the gut membrane only delivers the drug to the hepatic portal vein. This vessel leads directly into the liver. Here, the drug faces hepatic first-pass metabolism. The liver contains a high concentration of metabolizing enzymes and efflux transporters designed to neutralize foreign compounds. Survival is quantified by intrinsic clearance, dictated by the affinity between the molecule and liver enzymes. Highly lipophilic drugs are most susceptible to rapid metabolism. The liver recognizes fat-soluble compounds and oxidizes them, making them hydrophilic for biliary excretion. Let's follow the molecules that survive the liver and enter systemic plasma circulation. In the blood, drugs physically attach to proteins like albumin. This process is known as plasma protein binding. This introduces a critical pharmacokinetic metric, the fraction unbound. Only the unbound, free fraction of the drug is pharmacologically active. Molecules stuck to albumin are too large to leave the vessels. Only the free molecules can leave the plasma to enter tissues. Where the free drug goes depends on the macroscopic composition of the tissues, specifically the ratios of fat, protein, and water. Chemists achieve target organ partitioning by matching the drug's lipophilicity and molecular weight to the specific tissue blood flow of the target area. Conversely, manipulating these properties prevents drugs from crossing restricted barriers. Highly polar molecules, for example, are physically restricted from crossing the lipid-dense blood-brain barrier. Systemic distribution is a numbers game governed by the fraction unbound. If too much drug is highly lipophilic and binds to plasma proteins, the volume of distribution fails, regardless of how much was absorbed in the gut. If the drug navigates distribution, it reaches the pharmacodynamic phase, interacting with a specific target, like a receptor, an enzyme, or nucleic acid, to exert its effect. Here, designers encounter the ionization paradox. The state required to reach the target is often the opposite of the state required to bind to it. Reaching the target through cell membranes relied on the unionized, neutral form of the molecule. Once inside the binding pocket, this unionized form establishes essential hydrogen bonds with the receptor. The paradox is that maximum receptor affinity often requires the molecule to be in its charged, ionized state. These electrostatic connections lock the molecule firmly into the receptor pocket. The acidity and basicity of the compound dictate this balance. These factors influence the absolute strength of the ionic bridges and the resulting therapeutic efficacy. An optimized drug acts as a physicochemical chameleon. It leverages its pKa to remain unionized during transit, yet ionizes precisely at the target site to lock into the receptor. Evaluating the viability of an orally administered compound depends on a strict predictive framework. A successful drug requires sufficient solubility to survive the GI tract and precise unionized lipophilicity to cross the intestinal membrane. It must have low intrinsic clearance to survive liver metabolism and a high fraction unbound to distribute through the plasma. Finally, it must possess an optimal pKa that allows for both target organ partitioning and immediate ionization upon entering the receptor binding pocket. Optimizing the interplay of pKa, lipophilicity, and solubility allows researchers to control drug behavior throughout the ADME cycle. These parameters determine whether a theoretical molecule can navigate the human body and reach its intended receptor.